Instructor. And good afternoon, everyone. And this is my pleasure to be here today to present our work at LVM-OCR. And for the better connection, I think please allow me to turn on the video. I think it's better. Yes.
Yes,
Yes.
yes, it is.
Uh,
I have already made you the post, so you can.
yes. Thank you for all for logging in and joining us today. And before we start the main topic about the area OCR, as you see and the schedule, we will start with an overview about optical character recognition. This is the main purpose. So you see, this is the OCR transform for optical character recognition. So you see, optical character recognition belongs to the family of techniques performing automatic identification. And so first, we discuss about some of the automatic identification. In the traditional way, we entering the data into a computer is through the keyboard, right? And however, this is not always the best nor the most efficient solution. In many cases, automatic identification may be an alternative, and various technologies for automatic identification exist, and they cover needs for different areas of application. And below, I will go through a brief overview of the different technologies and their application is given. So the first is the speech recognition, right? And in the system for speech recognition, spoken input from the predefined library of words are recognized. Such systems should be speaker independent and may be used, for instance, for reservation or ordering a goods by telephone. Another kind of such system are those used to recognize the speaker rather than words, or for the identification. Second is about the radio frequency. This kind of identification is used, for instance, in connection with toll roads for identification of cars. Special equipment on the car emits the information. The identification is efficient, but special equipment is needed both to send and to read the information. The information is also inaccessible to human. The third thing is the vision system. By the use of TV camera, objects may be identified by their shape or size. This approach may, for instance, be used in automation for recalculation or of the bottles or something like that. The type of bottles must be recognized, and the amount reimbursed for the bottle depends on its type. Next thing is the magnetic magnetic stripe, you see. And information contained in magnetic stripes are widely used on credit cards, X. So what a large amount of information can be stored on the magnetic stripe, like the cards that we can input, like in the car parking or to access some building, to, but specially designed that to the design readers are required, then the information cannot be read by humans. So is we have the machine to read that by the swipe on the machine, and we can read the whole data in the magnetic stripe, right? And next thing is the barcode for identification. So the barcode consists of several dark and light lines representing a binary code for an 11, somewhat like 11 digits number, 10 of which identify the particular product. We can see that almost in the supermarket or anything where else, many places, right, in the barcode. So the barcodes are read optically when the product moves over the glass window by the focus laser beam of weak intensity, which is swept across the glass window in a specially designed scanning pattern. the reflect line is measured and analyzed by the computer. Due to early standardization, barcodes are today widely used and constitute about 60% of the total market for automatic identification, especially for when we're counting for the bill, right? And next thing is the magnetic ink. Magnetic ink. So printing in magnetic ink is mainly used with bank applications. The characters are written in ink that contains finely ground material, and they are written in star font, which is specially designed for the application. And before the characters are read, the ink is exposed to the magnetic field. This process accentuates each character and helps simplify the detection. The characters are read by interpreting the waveform obtained when scanned the character horizontally. Each character is designed to have its own specific waveform. Although designed for machine reading, the characters are still readable to humans. However, the reading is dependent on the character being printed with the magnetic ink. And next thing we go through to our topic today. So it's about the optical mark reading. This technology is due to register location of marks. It may be used to read forms where the information is given by marking predefined alternative. Such forms will also readable to humans, and this approach may be efficient when the input is constant and may be predefined, and there's either a fixed number or alternative. And the last one we use today is the optical character recognition. I mean the OCR, as we see a lot today. So optical character recognition is needed when the information should be readable both to human and to the machines, and alternative inputs cannot be redefined. In comparison with the other techniques for automatic identification, optical character recognition is unique in that it does not require control of the process that produces the information. So we see here is the a typical OCR system. A typical OCR system consists of several components. In the figure you see, there's a bunch of the segment. So bunch of components. In the figure you see the common setup is illustrated. The first step is the process is to digitize the analog document using an optical scanner, right? And when the regions contain text are located, each symbol will be extracted through a segmentation process. After that, the extracted symbol may then be preprocessed, eliminates noise to facilitate the extraction of features in the next step. So the identity of each symbol is found by comparing the extracted feature with description of the symbol classes obtained through a previous learning phrase. So, and finally, contextual information is used to reconstruct the words and number of the original text. And in the next section, these steps and some other methods involved are described in more detail. So first, we discussed about like the optical scanning, right? I mean, this is an optical scanning. It's just an animation for that. So we see here, I mean, this, let's see, we'll go through that swiftly and go to, okay. So this is optical scanning. Through the scanning process, a digital image of the original document is captured. And in OCR optical scanner are used, which generally consists of transport mechanism plus a sensing device that converts light intensity into gray levels. Printed document usually consists of black print on a white background, right? Hence, When performing OCR, it is common practice to convert the multi-level image into a bi-level image of black and white. We don't use any other color. We just use black and white for the easier read. So often this process, known as thresholding, is performed on the scanner to save memory spaces and computational effort. The thresholding process is important as a result of the following recognition is totally depend on the quality of the bi-level image. Still, the thresholding performed on the scanner is usually very simple. The fixed threshold is used, and when placed grade levels below, this threshold is set to be black and level above are set to be white. For the high contrast document with uniform background, the chosen fixed threshold can be sufficient. And however, a lot of documents encountered in practice have a rather large trend in contrast. In these cases, more sophisticated methods for thresholding are required to attain a good results. As you can see here in the briefly, it's about the problem in thresholding. We have three images in the top, in the middle, and the bottom. You see in the top, original grade level image is the original, right? When we use the image threshold with the global method, if we like this, you can see we can't see a lot of things like this in the left part. We miss everything. In the bottom, you see when we use with an adaptive method, we can see it clearly a little bit. And it's only have the black and white. It's very clearly. And that's why we can even more readable for the machine, not just by a human. We aim to the computer can read that. Okay, so this is about the local segmentation phase, right? So in the segmentation, this is a process that determines the constituents of an image. Is it necessary to locate the region of the document where data have been printed and distinguish them from figure or graphics? For instance, when performing automatic mail sorting, an address must be located and separated from other print on the enveloped, like stamps or company logo or something, or prior to recognition. Applied to text, segmentation is the isolation of character word, and the method of optical character recognition algorithm segment the word into isolated character which are recognized individually. Usually, this segmentation is performed by isolating each connected component that is each connected black area, and this technique is easy to implement, but problem occur if character touch or if like character are fragmented and consist of several parts. And the main problem is segmentation may be divided into four groups. First is extraction of touching and fragmented character. A second is distinguish noise from text. The third one is mistaking graphics or geometry for text. And the last one is mistaking text from graphics or geometry. Right? Then here you can see the degraded symbols when we use on the task of local segmentation. Okay. Here in the pre-processing, the image resulting from the scanning process that may contain a certain amount of noise, right? So depending on the resolution of the scanner and the success of applied technique for the thresholding, the character may be smeared or broken. Some of these defects, which may later cause poor recognition rates, can be eliminated by using a preprocessor to smooth the digitized character. As we learn from the data analysis, data mining, right? We have the clue that garbage in and garbage out. So we want the output is perfect. So we have to preprocess the input to be better. And coming through the model, and after the model, we do have to use like post-processing, as I will tell you after this. Okay, so in addition to smoothing, reprocessing usually include normalization. And you can see the normalization is applied to obtain character of uniform size, slant, and rotation. To be able to correct for rotation, the angle of rotation must be found. For rotated page and lines of text, variants of Hodge transform are commonly used for detecting scale. However, to find the rotation angle of a single symbol is not possible until after the symbol has been recognized. And next we go through like the feature extraction. The object of feature extraction is to capture the essential characteristic of the symbol, and it is generally accepted that this is one of the most difficult problems of pattern recognition. The most straightforward way to describing a character is by the actual raster image. Another approach is to extract certain features that still characterize the symbols, but leaves out the unimportant attributes. The techniques for extraction of such feature are often divided into three main groups, where the features are found from the distribution of point. Okay, and the transformation and series expansion, and the last one is structural analysis. So we go coming through to that. It's about like, let me go briefly for that. Let's see. I said about the robustness. We have 5 points here. It's about the noise. So it's about like sensitivity to disconnected line segment, bumps, gaps, fill-ups, etc. And second is a distortion. Sensitivity to local variance like rounded corners, improper protrusions, dilations, and shrinkage. The third is the style variation. Sensitivity to variation in style, like the use of different shapes to represent the same character, or the use of serifs, slangs, and many other, so on. The fourth will be the translation. Sensitivity to the movement of the whole character or its component. And the last one is rotation. Sensitivity to change in orientation of the character, right? And for the practical use, we have three things. So first is the speed of the recognition. Second is the complexity of implementation. And the third will be independence. So we need the supplementary techniques, right? And each of the techniques evaluated in table, you can see are described in the section like this. And you can see is about the template matching, right? Template matching. These techniques are different from other in that no feature are actually extracted, right? And instead of matrix containing the image or the input character is directly matched with the set of prototype character representing each possible class. The distance between the pattern and each prototype is computed, and the class of prototype giving the best mark is assigned to the pattern. It's about a feature-based technique. So in these methods of the feature-based techniques, the significant measurement are calculated and extracted from the character and compared to the description of the character classes obtained during the training phase. The description that must most closely provides recognition. The feature are given as number in the feature vector, and this feature vector is U represent the symbol. Next, we see about the transformation. Okay, so it's about the zoning, right? Okay, let's go through the next part. Is the next component is about like feature extraction, right? We will go through the classification. Here's a stroke extract from the capital letter, and you can see the F, H, and N right here. Okay, let's say it about like the classification or the recognition in the form above in the previous session. Okay, so here is the classification. Is the main things that we want to focus, right? The classification is the process of identifying each character and assigning it to the correct character class, right? For the text recognition. And in the following section, two different approach for classification in character recognition are discussed about like decision theoretic method and a structural method. You can see on the screen. And we may also have pattern characteristic derived from the physical structure of the character, which are not as easily quantified. And in these cases, the relationship between the characteristic may be important when deciding on class membership. For instance, if we know that the character consists of one vertical and one horizontal stroke, it may be either an L or a T. And the relationship between two strokes is needed to distinguish the character. A structural approach is then needed. So it's about we go through the decision theoretic method. The principal approach to decision theoretic recognition are the the distance classifier, minimum distance classifiers, right? For the statistical classifier and neural network also. Each of these classification techniques are briefly described. So first is about matching. Matching covers a group of techniques based on similarity measure where the distance between the feature vector describing the extracted character and the description of each class is calculated. Different measure may be used, but the common is the Euclid system. Distance. This minimum distance classifier works well when the classes are well separated. That is when the distance between the means is large compared to the spread of each classes. Okay, so let's say about the optimum statistical classifier. In this statistical classification of the probabilistic approach to recognize is applied. The idea is to use the classification schema that is optimal in the sense that, on average, its use gives the lowest probability of making classification error. And we use the Bayes classifier, the Bayes classifier, right? Second, the third thing is about the neural network. We use a lot today words. And recently, you can see the use of neural networks to recognize a character and other types of pattern also has resurfaced. Considering the backpropagation network, this network is composed of several layers of interconnected elements, and a feature vector enters the network at the input layer. Each element of the layer computes a weighted sum of its input and transform it into an output by the non-linear function. During training, the weights at each connection are adjusted until the desired output is obtained. A problem of neural network in OCR may be their limited predictability and generality, while an advantage is their adaptive nature. It's about the structure method. Within the area of structural recognition, syntactic Syntactic methods are among the most prevalent approach. Other techniques exist, but they are less general and will be not repeated here. So it's about the syntactic methods, measures of similarity based on relationships between structural component may be formulated by using grammatical concept. The idea is that a class has its own grammar define the composition of the character, and a grammar may be represented as a string or a trees or something, and the structure component extracted from an unknown character is matched against with the grammars of its classes. Suppose that we have two different character classes which can be generated by the two grammar G1 and G2 respectively. So given an unknown character, we say that it is more similar to the first class if it may be generated by the grammar G1 but not by G2. And we go through the last component. It's about the post-processing after classification, right? So we use like the grouping and error detection we discussed, right? Error detection and correction. So the first grouping, the result of the plane's symbol recognition on the document is a set of individual symbols. So, however, these symbols in themselves do usually not contain enough information. Instead, we would like to associate the individual symbol, like to combine them, that belong to the same string with each other, making a works and number. And the process of performing this association of symbol into string is commonly referred to as grouping. The grouping of the symbol into strings is based on the symbol location in the document. Symbols that are found to be sufficiently close are grouped together. It's like we use the k-mean or something like that. We have the distance close together and we group that into together. For fonts with fixed pitch, the process of grouping is very easy as the position of each character is known. For typeset character, the distance between characters are variable. However, the distance between words are usually significantly larger than the distance between characters, and grouping is therefore still possible. And the real problem occurs for handwritten character or when the text is code. Okay, so how about error detection and correction? Up until the grouping, each character has been treated separately. The context in which each character appears has usually not been exploited. However, in advanced article text recognition problem, a system consisting only a single character recognition will be not sufficient. Even the best recognition system will not give 100% correct identification of all characters, but some of these errors may be detected or even corrected by the user in the context. And especially we use on the team today is about the medical. Especially if just a small mistake will lead to the leave of anyone. And so there are two main approaches where the first utilize the possibility of sequence of the character appearing together. This may be done by the use of rules defining the syntax of the word by saying, for instance, that after a period that should usually be a capital letter. Also, for different languages and probabilities of two or more characters appear together in a sequence can be computed and may be utilized to detect errors. And for instance, in the English language, the probability of the K appearing after an H is a word is error. And if such a combination is detected, an error is assumed. And another approach is the use of dictionaries, which has proven to be the most efficient method for error detection and correction. Giving a word in which an error may be present, like we use a Grammarly, right? when writing something and the grammar, we will check that if it have a mistake or something, they will let us fix that. They will guide us. So if the word is not in the dictionary, so what about that? An error has been detected and may be corrected by changing the word into the more similar word. Probability obtained from the classification may have to identify the character which has been erroneously classified. If the word is present in the dictionary, this does importantly not prove that no error occurred. An error may be transformed the word from one legal word to another, and such errors are undetectable by this product. And the disadvantage of the dictionary methods is that the searches and comparison implying are time consuming, consuming, right? And let's talk about a little bit about the application of OCR. We use it in the data entries. This error covered technology for entering large amount of restricted data. Initial such document reading machine was used for banking application or something like that. How about the text entry? The second branch of a reading machine is that the page reader for text entry, mainly used in office automation. As I don't know in your country, but in our country, we are now focused on the digital transformation. We try to store on the document into digital thing, like the bunch of papers that store in the past, and we try to store in the database for searching for the latest support for patrons answer, something like that. So that's about the text entry. And the third is about the process automation. Process automation. Within this area of application, the main concern is not to read what is printed, but rather to control some particular process. This is actually the technology of automatic address reading for mail sorting. Hence, the goal is to direct each letter into the appropriate bin regardless of whether each character was correctly recognized or not. The general approach is to read on the information available and use the postcode as the redundancy check. The acceptance rate of this system is obviously very dependent on the properties of the mail. This rate therefore varies with the percentage of handwritten email. Although the reject rate for mail sorting may be large, the missort rate is usually close to zero. The sorting speed is typically about like 30,000 letters per hour. So that much, right? Let's say about many other applications for from the OCR. So the above areas are the ones in which OCR has been most successful and most widely used. However, many other areas of application exist, and some of these are mentioned. So first is Ed for Blind. In the early days, before the digital computers and the need for input of large amount of data emerged, this was immediate area of application for reading machines, combined with the speech synthesis system, such a reader would enable the blind to understand like the printed document. However, a problem has been the high cost and reading machines, but this may be an increasing area at the cost of the microelectronics problem. Second is about the automatic number plate reader for traffic, and also I have the previous article about I mean the meter, the water meter reading, just published, and you can see in my Scholar. And those are some of the OCR application. So say about the automatic number plate reader. A few systems for automatic reading of number plate of cars and motorbike also exist, as opposed to other application of OCR. The input image is not a natural binary image. and must be captured by the very fast camera. As you can see, when we capture, when we want to take photo for another people, like our lover or someone other, for your wife or someone, maybe they will say that, oh, it's really ugly. This will be like, why don't you capture in this size or in this area or something like that. So that's a huge problem when we capture the things like, and go to the automatic number plate reader. So it will be very fast because the vehicle is running on the road, and we need to capture if they're like passing the traffic light or something. So we will give them a penalty. So this will be captured from the very fast camera, right? This creates a special problem. And sorry, so maybe you have some question? Miss Sadwick, Satya? Uh, okay, so we have we also have uh the like the QA session, so we will discuss about the things later. Okay, so let's say I will go through the main topic today. It's just an overview of OCR that we try to know a little bit about the technique, a traditional technique. So, okay, so let me ask you the quick question. Can you just like raise hand button or type yes in the chat box? That just like this. When you go to the hospital, and then how many of you have ever tried to read a doctor handwritten prescription and don't know what he or she write because it's too like, I don't know, it's just like very ugly or something? Have you ever had anyone? Yes, right? So I see a lot of like, yes, I see a lot of yes, and I'm not surprised. I've been too. It happens to all of us. We all know the struggle. The doctor handwritten is often like not way somewhere, right? Let's just say it can be very messy, crippled, or sometimes looks like a completely different languages. I don't know. It's just like he live in another language or something. But to be fair to the doctors, there is the reason for this, right? It's in the nature of their job. They are under high pressure and have to see so many patients every single day. So they have to write prescription very quickly to save time for the next person. So they prioritize the speed over beauty. Don't like us, right? That's why the text is often so careless and hard to read. So now here's the big problem we face today. We are trying to move toward digital health, scanning these old paper records into the computer. So if we are humans, with our human intuition, struggle to read this messy handwriting, so how can we expect a computer to read that? A traditional computer program usually failed because they look for the perfect letters, like we use the traditional OCR at the previous I said. But the medical records are rarely perfect. So how do we solve this? How do we teach our machines to guess and understand message text just like the pharmacist does? So that's exactly what we will discuss today. And I was very excited to share with you our article, our works have just presented a previous international conference on Indonesia. It may be in a couple of weeks ago. Okay, so this is about the LVM-OCR, a transformer-based architecture for context-aware document understanding. We are on from the Open University in Vietnam. So in the next few minutes, we will explore how we are moving from simple text recognition to the new visual comprehension, especially in the medical field. We don't just extract the text. We try to like know exactly what the contexts are. And that's our goal, right? Especially now you can see that a lot of chatbots like Gemini, ChatGPT, when you just capture the capture the screen and just put into the chat box and just hit enter, and just ask them to extract the home text. They did extract the home text in the perfect way, right? But some of the problem is may occur because that is multi-model. So some of the difficulty input, maybe they will not give us a perfect answer. So let's say this is our key point. That leads us to the key point of our research. So first, let's talk about context. We are living in the era of digital health. Every hospital wants to move away from paper and go completely digital. That's why we use a lot of apps, right? And in our country, we are trying to transform everything. Like now we just have one application to manage the whole citizen all over the country. And you can see in the next few years, I think in the vision of the government, they want to like integrate like the bank account and everything on that. Yeah. So that's our like the trending. I don't know in your country, but that's the effect in our country right now. So every hospital want to move away from paper and go completely digital, right? And imagine a world when the doctor can search for the patient's history from 20 years ago with just one click. That's the dream of the digital transformation. And let's talk about the problem occur. The problem. But there is a huge block. We have millions of medical documents that are not digital. They are handwritten prescription. As you can see, we cannot read by our eyes. But now, for the better efficient, we have to train the computer to read that instead of us. It takes a lot of time for us, and even we cannot have ability to do that. So there's a lot of handwritten prescription, century-old medical manuscript, or patient records that have been sitting in a damp warehouse for decades. These documents are often torn, yellowed, or faded. So the big question is, how do we digitize them? If we use standard tools, they fail. Like we use the OCR, the Chinese, we cannot extract that because it's looking for the perfect input. So they just see the noise, not text. So here how our solution. We introduce LVM-OCR. Think of LVM-OCR as a smart reader. It uses the power of large vision models, similar to the technology behind AI art or advanced robots. Unlike our system that simply try to match shapes, pattern matching, like we discussed in the previous slide, our model tries to understand the context. It reads the document like human expert would, looking at the home page to make sense of the message details. So how exactly does it do that? Let's look at the technology behind it. So we have the messy, difficult to read medical document, right? Like this. Maybe is the good one. It's not hard to read, but in the real world, it's maybe worse than that, right? So difficult to read the medical document. So you might be wondering, why can't we just use standard OCR software? We had an OCR technology for decades, right? To understand why our new solution works, we first need to understand why the old girl failed. For a long time, the industry standard relied heavily on convolutional neural network, or we know that CNNs, right? Let's see all of this. Okay, so combined with the rigid handcrafts rules. Now, I don't want to bore you with hairy math, but I want you to visualize how the standard CNN reads the document. Imagine you are trying to read a large newspapers. and you are forced to look through a tiny paper tip, like we just read like by pixel, like in this area, and just go through like from left to right, left to right, left to right, left to right. But we cannot look at the whole papers. Okay, so you can only see the small circle of the page at a time. You slide this tip across the page inch by inch. We call this the keyhole effect. Keyhole effect. The AI is looking at the document through this tiny keyhole. When it hovers over the curve, it thinks, okay, that looks like the letter C. When it moves to the vertical line, it decides that might be letter I or a number one. I don't know. It is making decisions based only on what it sees in that tiny isolated window. And this led to the filter flow. It lacks global context because the model is so obsessed with the tiny detail inside the keyhole. It's completely missed the bigger feature in the context, the global context. It doesn't know that the C is just found in the actual part of the word cancer, something like that. It doesn't realize that this text is located in the diagnosis section of the page rather than the patient name section. It's reading letters, but it isn't reading the story. So now let's bring back to our messy medical record. If you have a clean, perfect digital PDF, the keyhole approach works fine, right? But what happens when the document is crumbed or the ink is faded from years of storage? When a fold in the paper cuts through a letter or the coffee stain covers part of the word, that local view breaks down completely. The CNN sees the broken line to get confused because it has no backup plan. No backup plan. Okay, so this is the confirmed receipt, right? So it can't look at the surrounding words to get the missing piece. Here you can see the symbol. So I want you to look closely at the image on the slide. Focus on an eyes only on that ink stroke right in the middle. If you look at just that specific spot, exactly like CNN does, it's meaningless, isn't it? It could be scratched, a smoker, or a letter. You can't tell. But if you zoom out and look at the home page layout, your human brain immediately realizes, that's it, a signature on the bottom of the phone. Something like this, right? It's just a signature. And that's a limitation we are facing. CNN's struggle to get this homepage view. And that is why they failed with medical record. This is really important, right? So if traditional CNNs are like looking at the word through a tiny keyhole, how do we fix that? We need an open door and see the whole room at once. This brings us to the core of our solution, the vision transformer. The vision transformer. Here is the fundamental shift in thinking, global perception. Unlike the old methods that scan an image pixel by pixel or region by region, the vision transformer takes a holistic approach. Imagine you are looking at a painting. You don't press your nose against the canvas and look at one brushstroke at a time. You step back. Okay, you see the whole scene at once, right? That's exactly what this model does. It's considered entire visual field simultaneously, allowing us to understand the relationship between the header and the top of the page and the footnote at the very bottom. Now, you may ask, how does the computer digest an entire page at once? It doesn't treat document as a giant flat sheet of pixels. Instead, it uses a technique called patch division. Think of it like language. When you read a book, you don't read a letter by letter. That you would be organizingly slow. Instead, your brain groups letter into words and words into sentence to derive meaning, right? And LVM-OCR does the exact same thing. It breaks the document image into small squares or patches, as we know in the model. Conceptually, each path is treated just like a word in a sentence. It's allowed the model to process the image as a sequence of meaningful information, not just random noise. So this leads to the mathematical foundation you see here. Don't let the math intimidate you. The concept is quite elegant. So the most critical part here is e-position, because the transformer look at their own patches at the same time, not in other. It needs a way to know where things are. This e-position terms acts like a GPS coordinate for every patches. It reserves the spatial structure, ensuring the model understands and the patient's name in the name box and the signature at the bottom, even though it's reading them both instantly. In summary, by treating the image like language, we allow the machine to understand the context, not just shapes. Okay, so now let's we open up with the black box and we see how LVM-OCR actually thinks. Okay, how does it turn a messy image into structured text? It's not a magic. It's a four-step journey. The process is from picture to meaning. Is that when we feed the document image, into the system. But here is the difference. Instead of scanning pixel by pixel like a photocopier, the model used the path division. And imagine taking a pair of skissers and cutting image into small and meaningful square of patches. This allows the computer to process the whole paper as one, rather than getting stuck on a single line. And this bucket enter the VIT core, Vision Transformer core. This is the brain of the operation. It consists of 12 layers of deep reasoning. Inside this layer, the model isn't just looking, it's analyzing relationship using multi-head attention. And it asks a question like, does it vertical line belong to the letter T? Or is it a part of the table border? Something like that. So finally, we have the decoder. The decoder takes on the visual reasoning and perform a cross-model translation, turning those abstraction visual features into readable text. Okay, so this is a compact view of the LVM-OCR character, and you can see here. Okay, and let's see about the key innovation. The decoder, okay. The key innovation. Why it works for medicine? So why does this matter for medical records? It comes down to two key innovations. So first, we use the hierarchical instruction. Medical documents are diverse, and we have the tiny text on pharmacy receipts and huge readers, the huge headers on hospital charts, right? Our model adapts its eyesight across the different scale, capturing both the fine details of the label and the big picture of the poster without losing clarity. And the second, perhaps the most importantly, that's the cross attention, as you can see in the picture. And this mechanism contextualizes every character. It looks the global surrounding the ink stroke and the global surrounding the sentence at the same time. To summarize this architecture, think a bit like the thoughtful human reader. It doesn't just stare at one letter. It glances at the home page first to understand the layout, then zoom in on specific region, and continuously cross-reference the context to make sure it understands exactly what the doctor wrote. Okay, and now let's move to the most critical part of our system, the brain behind the operation. We call it smart attention. To understand why we built this, I want you to imagine a very specific, dangerous scenario. We are looking at a faded old medical record. you see a vertical line, and we have, you have a question. Is it a number 1 or is it the lowercase letter I? It's a normal sentence. Confusing dumb is just a typo. But in the medical prescription, mistaking a dosage unit or a patient ID could be catastrophic, right? The traditional AI looks at the vertical line, analyzes the pixel, sees that the ink is faded, and frankly, it gets confused, and it guesses, and it guesses. It's like the chatbot AIs right now. If you ask them something they don't know, they will answer like they know exactly the thing, but it's absolutely wrong, right? When we ask ChatGPT something about something that just happened previous minutes ago, they don't know, but they still answer this us, right? Something like that. So that's a big problem, and especially in the team of medical things. And how does, a traditional AI look at the vertical line side and analyze the pixel. So see the ink faded and brain leak, and it gets confused. It will guesses. So how does a human, like the pharmacist, solve this? A pharmacist doesn't just stare at the ink. They use the context, the global context that the previous I saw. If that vertical line is followed by MG, they know it's the likely a number. If it's in the middle of the word, like clinic, they know it's a letter, right? We have an I inside the clinic, something like that. So we want our model to mimic this human behavior. We call this linguistic bias. Linguistic bias. We stopped trying to make the machine just see better and started teaching it to read better using the same directional and structural cues that you and I use. This logic is beautifully captured in this equation. You can see here the smart attention with the Q, K, V, and we have the submat, and especially the things where linguistic encodes reading order and word spacing cues. Okay, so if we look at the formula, you see the standard attention mechanism. That's in the visual part. But look at the edit, this term. That's in the M linguistic. Think of M linguistic as a guide or a cheat sheet embedded right into the math. It encodes the rules of the language, like the fact that we read from left to right and that certain letters usually appear together. So when the visual part say, I'm not sure what this blurry pixel is, the linguistic turn steps in and says, based on the surrounding letter and the facing and the spacing, this must be an I, not a number 1. Okay, so in a sense, this mechanism allows the system to stop guessing pixel and start disambiguating the text based on context. It effectively gives our AI the intuition of an experienced pharmacist deciphering a doctor handwritten, right? Okay, so let's see. So we have to build a powerful architecture, a smart friend for our system. But as any teacher knows, a smart student still needs the right education to succeed in the real world. That brings us to training strategy, which we call learning from imperfection. You see, if we only train the model on clean, perfect digital fonts, it will be felt the moment it sees a real dirty hospital record. So instead of hiding the mess, we intentionally create it. So we use the algorithm intelligent document augmentation. Think of this like the flight simulator for the AI. We force the model to practice on the damaged documents so it doesn't get confused later. We simulate the life cycle of the physical document. First, we apply the random rotation of plus or minus 5 degrees. Why? Because nurse and doctor rarely scan paper perfectly straight. Right? Something is depend on they are going very fast and they're just copying to putting into the scan machine and don't have time to fix the position. So that will be I have the rotation. So we add the noise in the next step. This mimics the statics and artifacts you get from the chip or out scanner found in many clinics. We even simulated physical damage with the 30% probability. We applied tier and weird patterns, teaching the model to read text even when the paper is ripped or crumbed. And most importantly, for historical archive, we simulated aging effects. We digitally yellowed the paper and faded the ink. This is crucial because it takes the model that a faded letter is still a letter. Now, how does the model learn from this chaotic data? Right, and that lies in our loss function. So here in the equation, you can see here. I won't bore you with the complex maths. Okay, so but I want you to understand the philosophy behind this equation. It's the balancing act between two goals. Precision. Now, the first part is the cross entropy or CTC loss, as we know. We parse the model to get the sequence of character right. It ensures that paracetamol is read in the correct order. Generalization. So this is about the second part, regularization. Prevent the model from overthinking or memorizing the noise we just added. It keeps the model flexible. Okay, so to summarize this slide, I want to summarize this by training on intentionally damaged data and using a balanced loss function, we are essentially vaccinating our model against the massive reality of the healthcare world. Let's say it's about the experimental setup. So now, how do we prove that this model actually works in science? We can't just claim our AI is smart, right? You have to put it into the religious exam phase. We didn't want to test LVM-OCR in a safe, controlled laboratory bubble. We wanted to throw it into the trials of the real world. So we selected 4 specific battlegrounds listed in here in the table 1, you can see, to represent the diverse challenges of the optical character recognition. Think of these datasets not just as finds, as the proxy of medical challenges. First, we have the IM dataset. This is a collection of handwritten personal notes, right? Personal notes. What is this here? Because as we discussed earlier, if the model can decipher these script notes, is ready to tackle the ultimate boss, the doctor handwritten on patient charts. So next we use the SROI. These are scans receipts. When a receipt is a medical record, it shares the same DNA. It has a complex structural layout with price, days, and items. If the model can understand a Kronberg supermarket receipt, it can understand the structural lab report or hospital invoice, right? And then we have the ICD AR 2019 and REX. These contain multilingual street text and bilingual signs. In a globalized healthcare system, patient records often contain mixed languages, Latin names for drugs, local language for instruction, and also the doctor language. These data sets test the model ability to switch language on the fly, right? And finally, how do we create the exam? We don't just look at the character accuracy. We is like simply checking the model spell the word right. We also measure word understanding and character accuracy and word understanding, right? You can see. So this is the difference between a student who memorized the textbooks and a student who actually understand the subject. We want to ensure our AI isn't just seeing letters, but comprehending the medical narrative. Let's say about the results, about a model, this search thing, like we are right the moment of the truth. We'll discuss the architecture and the regardless training. But the real question is, does it actually work better than what we already have, like traditional OCR as the beginning? So if you look at the table 2, don't just see it as a list number, view it as the timeline of evolution of computer vision. You can say here from CNN to Aster to SAR to Transformer OCR to like the LVM-OCR in else. So let's look back on 2017. The industry standard was CRNN. It has a character error rate of over 8%. In a cancer email, 8% is annoying, but in a hospital, you can see an 80% error rate is really dangerous. It means nearly 1 out of every 10 character is wrong. That's the difference between 10 milligram and 100 milligram or something like that. Over the years, models like Aster and SAR chipped away at this error. They came Transformer OCR, Transformer Optical Character Recognition. That's a combination of Transformer with Optical Character Recognition. We have the TR-OCR. In 2023, a PowerPoint Transformer model that brought the error down to 4.86%. It was massively forward. But with LVM-OCR, we have pushed the boundary even further. We achieved a character error rate which is 4.12%. This is the lowest among all major models. But here the statistic I want to focus on, the word error rate. The word error rate. Okay, so notice that while our character error dropped slightly compared to Transformer OCR, our word error rate dropped significantly to 12.38. You can see it's a word error. So the minor is the better. You can see the smaller is the better for the word error. Okay, for the character error also. About recent recall. So the character is better also. Okay, so let's go through that. So we don't misunderstand it. So why is this gap important? So it proves that our model isn't just guessing a letter better. It's understanding the words better because of the smart attention. And we can see that's the frame of our model. Mechanism that we discussed earlier. So even the model is unsure about single fuzzy letter. It's due to the context of the whole word to get the right answer. And finally, with the precision of 94.8% and recall of 94.2%, we have a system that is not only accurate, but incredibly consistent. We haven't just built a model that matched the state of the art. We had to build one that consistently outperform it, making it safer and more reliable for biomedical application. So as a part of our research is when we go to the experimentation, so we know the system works, but as an engineer and scientist, we shouldn't just happy at this work. We need to know why it works. To find out, we perform the ablation study. Think of it as a constructive sabotage. We deliberate turn off specific parts of our system one by one to see how much the performance would drop. This tells us which components are truly essential. So first we ask, is our training strategy really that important? So we turn on the data augmentation, the part where we simulate yellow paper and scanning noise. The result is shocking, as you can see. The error is plus 42%. And this is a massive finding. It proves that the medical document having a smart model isn't enough. It must teach that model to survive in the messy environment. Without those simulation of old worn-out paper, the model simply cannot handle real-world data. And next, we test the architecture itself. We remove the cross-attention mechanism and bridge that connects the visual image to the textual understanding. Immediately, errors spike by 27%. You can see. This confirms that you can't just treat this as a simple image recognition task. The model needs that deep connection between seeing the pixels and understanding the language context is to be accurate. So what is the takeaway from this table? It tells that LVM-OCR is not a magic stick. It's a carefully balanced system. Whether it's the text-aware attention or the multi-scale training, every single component plays a critical role. And if you remove even one piece, the whole system becomes significantly less effective. So let's talk about like a lot of error rate. But in the hospital, a low error rate doesn't matter if the AI cannot handle the variety of documents you threw at it, right? So let's look at the qualitative advantage, or simply put, the talents of this model. First, we think about a typical medical lab report. It's never just a simple paragraph. It's a full of complex layout, intervening columns, tiny footnotes, and messy table. Most AI gets confused here, but because the LVM-OCR understands the whole page at once, it can untangle these layouts with 92.3% in accuracy. Okay, so it's also the polyglot. So in our global world, a doctor might encounter a patient record in Chinese or a drug level in Arabic or something like that. This model has a strong multilingual capability, keeping errors very low at 5.2%, no matter that is strip. So next we have the time syncability, right? When we're dealing with historical document, we saw a massive 23% improvement. Okay, so this is crucial. It means the model can look past the fading ink and the yellowing paper to recover lost medical history. And now you might be thinking, a model this smart must be very slow and heavy, right? Let's look at the table 4. Table 4. This is the efficiency test. On the top, we have the CRNN. It's very fast, right? It's very fast, with just 12.3 milliseconds. But is it too simple and makes mistakes, right? At the previous table, you see, in the middle, we have the transformer OCR. It's a PowerPoint, but it's huge and slow. But you can see, it takes a lot of time to separate, and parameters is over 300 million parameters. You can see like this, and okay. And about LVM-OCR is the sweet spot, right? This is the balancing. We try to speed up than transformer OCR, but we try to have the more accuracy than the CRNN, and we have a balanced one. Okay, so that's the sweet spot. It used 186 million parameters, making it much lighter than transformer OCR. And with a speed of 43.2 millisecond per image. It's fast enough to be used in real-world software without keeping the doctor waiting. So in summary, it's smart enough to understand complex page, but light enough to run efficiently. How do we apply LVM-OCR in healthcare? So we have seen the math and the error rate. But the most important question is, how does it actually help a doctor or a researcher in the real world? We have identified 3 specific scenarios where LVM-OCR changed the game. So first, let's look at the past. Medical knowledge is new. We have the libraries for full century-old manuscript that are literally falling apart, weathered by time and fading away. A standard scanner often failed here because they treat strings and Wincode as text. Our model, however, can look past the damage by accurately digitize these documents. We are not just saving paper, we are preserving medical heritage and making ancient treatments searchable for the first time. And next, we move to the present. Inside a busy hospital, think about the lab report or the blood test result. It's never just a simple paragraph. It's a messy mix of intervening columns, tables, and tiny footnotes at the bottom. A regular computer reads this line by line and gets confused. But because our model sees the whole picture, it sustains a 92.3% accuracy even on these dense materials. It knows exactly which number belongs to which column. So finally, we look at the global context. In pharmaceutical settings, when traveling, we often encounter street signs or medical labels in unfamiliar language. This can be dangerous if misread. Our model offers strong generation across diverse linguistic systems, whether label is in English, Arabic, Chinese, any others. So the system provides a reliable reading, ensuring safety across borders. Here's a picture of the document understanding. As we reach the end of our presentation, let's summarize what this all means. So reaching the gap, so the LVM-OCR represent a turning point. We are no longer just teaching computer to recognize steps. We are teaching them to understand meaning. It bridges the gap between simple perception, just seeing the pixel, and true comprehension. This moves us one step closer to human-like reading. Most importantly, it excels exactly where we need it most, deciphering the degrade, messy, and complex layout that have the confused traditional system for decades. And for the future direction, but we are not stopping here, right? We have a clear roadmap in the future. First, we want to make this technology portable. Currently, these models are very large, as you see. Our goal is to develop the lightweight variants. Imagine a world where the doctor doesn't need a big server. They can use a simple handheld medical scanner, or even their smartphone to digitize the patient record instantly. We want to reduce computational costs to make this possible. Second, we believe in the specialization. We are looking into the domain specific for tuning, just like human reading, just like the human student choosing a major. We can change this model to become an expert, especially for medical records, legal contract, or historical archives. This ensures the highest possible accuracy for the professional who need it most. And the future is not just about smarter AI, it's about accessible and specialized AI that serves real human needs. Yes. So this brings us to the end of our presentation. Thank you very much for your attention. And if there is one key takeaway from our research, it is this. For decades, machines have been merely looking at document, but with LVM-OCR, we are finally teaching them to read like us. We believe this technology advanced OCR from simple recognition, just matching pixel patterns, to true visual understanding. And this shift is what will finally allow us to unlock the valuable data hidden in millions of medical records around the world. And I hope you found this topic as exciting as we do. And so I'm now happy to answer any question you may have. Let me go to
Yeah.
have this
Any
board.
questions? Beck, can you have you uploaded this code in GitHub? Your this LBM OCR code is available in GitHub? No.
Yes, due to the term of things, like currently we are processed to publish the article, so maybe after we publish the article, I will send the GitHub to Dr.
Okay,
Sajab, and
because if the
they
students
can,
want to do some work, if you can
yeah,
share the GitHub link as well as paper,
yeah,
I can share with the students. So if anyone interested to do any kind of advanced OCR, because in India also lots of manuscripts are there, which require to be digitized. So anyway, so
yes.
question from Arka. Yes, yes, Arka.
I think many students they want to
Okay,
ask.
okay, fine. So unmute here. Okay, 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 sorry. Arka, you can. Yes, now you can unmute yourself. Yeah.
Good evening, Professor.
Yes. Hello.
Uh, Hello. I want to ask that, could you elaborate more on how your model could be like applied to like specific health concerns? Like, let's say, so like it is mostly focused on like how medical documents can be more clearly analyzed, right? If I understood correctly.
Not exactly, Arka, not exactly analyzed, because analyzed thing is something different. So here
Not
he,
analyzed, but like more extracting the text of the document when
yes,
from the
yes,
handwriting. Yeah.
yes, yes. Moreover, it is focusing on the OCR. So how it is going
So
to be? Yeah,
yes,
tell me.
yes.
Our
So I
aim is
want to
to
ask.
do everything
Yeah.
with OCR from, at the previous I have published some of the article about like water meter reading and handwritten
Okay.
mathematical also, and many else. So as I concern in this article is about like applying OCR with the transformer, with the recent transformer to apply it in various field, including the healthcare documents, anything others. So it will be a
Okay.
wide variant. And it's also my PhD topic. Yes.
Okay.
Yes,
Got it.
Kusagra. Kusagra, any questions?
Yeah, so once we have like the model and we have the data, as we can see, we can fine-tune on that. We're just giving the specific data set and we change them because we have changed in a lot of type of data from this receipt and handwriting text and many other like street side and many others. So they have wide range of learning process. So I think it will be the most popular for you to fight on that. Yeah, so please say your question.
Yes, Kusagra. Yeah.
Yes, sir. Good afternoon, sir. Sir, my question is that in medical documents, often it contains handwritten notes or a prescription or low quality scans. So, my question is how well do context aware OCR handles such variability in real healthcare setting? Because we know that healthcare documents are often noisy and inconsistent, and reliability is critical. So, how do we handle this accuracy versus those trade off things, low quality things?
Yes, thank you for such a directly like important question. As I saw in the previous at the ablation study, you can see when I removed augmentation. This is augmentation when we trying to do the things for the better result of the input image. That's a from the preprocessed image. You can see when we remove the augmentation, it's the errors plus 42%. So this is how we do the augmentation to make the input better for the model. You see, and basically it from here the smart testing, and also is the home architecture. You can see here, and the smart testing is the most powerful thing for our model. Are you clear with that? We do
Yes,
the
sir.
augmentation, yes. So we cannot like ablation the augmentation. We cannot leave that. And also two things here we do on the ablation. Yes, the augmentation and the cross attention. Those on very powerful things. So that's the augmentation, the part where I simulate yellow paper and scanning noise, right?
Fine, sir.
Yes. Thank you for your
Okay,
question.
Yatharth. Last question from Yatharth. Yes.
Hey, sir. So, thank you for such a good presentation. And I found the patch segmentation mechanism that you have implemented quite interesting. But while I was listening to your explanations and how it works, I thought of an example that if there is a document, and for example, documents don't always have all the necessary information in perceivable sentences. Sometimes there can be an important signature or a signatory name which can be at the bottom right corner of the page. So, won't your spatial recognition exclude that? And have you come across this problem? Thank you.
Yes, that's really like the tough question, So it's about it's really important from the input, as I mentioned in the previous from the beginning. So as we know from the data mining subject, right? The garbage in is about the garbage out. So the input is image. The input data is really important, and when we capture the image from the document that we want to process to extract the text, something like that, we have to like have the model a little bit before they coming through the pre-processing. We do have the pre-processing in the model, but we can have the model a little bit from the beginning. We capture with more like more beautiful or something like that input so that the model can read easily. So let's say is about the pre-processing. We had a path vision, so we had a spatial segmentation. As we see that it's different from the traditional OCR, is look through like the small patches, the small pixel. But in our model, it's look the whole picture of the content and the whole context. So we know exactly by using the VIT core and also the smart attention, right? So it will be know exactly the context, and it do have the error rate, as you can see in the table at the last thing. So I mean, it will have the error, but when it have the noise data, as will better for the traditional OCR system, but it still face a lot of problem when even a human, we cannot read it easily, right? So when it comes to the computer, it's also facing that problem too. So it's about like when we have when we try to have the model a little bit before, we try to make the input more clearer and giving the clearer input, we have the more perfect answer. I mean the output, the better output.
Understood. Thank you.
Yeah, thank you. So it's just AR, and it's like a lot of people are, at previous I attending in the international conference on the Open University of the Asia, and they are all talk about AI, and it's like every people are now depend on AI and think about AI. It's a powerful thing, and they can do anything, and they can replace us, but actually not. They're just like our partner that help us to work more efficiently. And for the medical context, they will help the doctor, but cannot replace the doctor. Because a doctor, they have to study for many years to get their certificate and to clarify all the things, right? To determine which medicine for which victim or something like that. So about our works OCR system, and just like the having the process to digitize the images into text is more efficiently and also faster. but cannot without a human observation. Yes.
Yes, I used. If you want, yeah.
Hello, sir.
Yes.
Sir, I have a question that you gave an example that in some cases the character seems to be similar, like one and I. So that same case gets to like if we see small l and caps I, they also seems to be similar. So there are the cases where our human brain itself fails to recognize the characters. So in that case, do we expect from the machines to recognize like those? How to dissimilar them?
Yes, thank you for the question again. So as I mentioned before, our model is not like the traditional OCR system. They just look at the pixel by pixel. But from our model, we look through the whole context. We focus on the global context. So it's about like the small things, right? It will be the letter with many other surrounding, like the word, as I mentioned in the previous example, like what is that? I just forgot. Something like clinic, right? Clinic or something like that. So we will try to extract the I letter from the clinic into text, and we are confused from I and number one, right? So our model look at the surrounding, look at another features, and look at another patch, not just like the pixel. So we know the context. This is the text is not a number. So is when it comes to combine with the context, we will determine it's a letter, it's not a number, something like that. So as I mentioned, it's also a parallel answer, but our model will be more powerful as we saw in the results, you see. And it look through the context. So it will be better for look through every like pixel by pixel for the traditional CNN, something like that. Yeah. So hopefully that may
Okay, is it clear?
Yes, sir. Thank you, sir.
yes, thank you.
So again, I am telling you, okay, any one of you, because see, we can generate lots of problem. Okay, so if you will contact Bay, he can having 4 to 5 different. So here you can use your own mother tongue also, because many of you here, Odisha, from Bengal, from other part of the country. So there are different prescriptions are there also. We can contact with the hospitals, like your government hospital, especially where they are still writing on this pen and paper. Doctors are writing. So we can collect that one and we can use how actually how that one particular code which is having bay. We can take the code and we can apply in our language. So how far it is working? Because many homeopathic doctors in Kolkata, I think they are still writing in Bengali. So yeah, yes or no. So any problem statement we can take and we'll try to solve that one in real life. And definitely in KIMS also will start same work. One work will be done on this because still doctors are writing in. You will go to the super hospitality or your OPD. So you know, what is that one? Super specialty, na? Yes, that one, or you can say go to the OPD. Still, doctors are writing in handwritten prescriptions. So we can collect those prescription either photocopy or your scan copy. Then let us implement with the code which is having Bay or other codes, and we can have one good work. Yes or no? Am I right or not?
Yes, sir.
So after the workshop or this winter school, we'll see how many problem statement we can derive and who will do that one. One to one, I'll try to assign that one. Okay, so in your studies, during the study also, or if you are free, say during Saturday, Sunday, those who have already working in company, if you want, then you can work on the live project. That's my plan actually. Okay, anyway, thank you very much, Ben. Hope your PhD will complete as soon as possible. And any one of the students will start any work on the OCR, definitely I'll be in contact with you and your guide, Dr. Bean. because Dr. Bin and me, we know each other for last 8 to 9 years. Okay, so I think we can have good collaboration. And thank you very much.
Yeah, thank you very much for having me today. It is my great honor to have the opportunity to work with you, and I hope for the near future we will have more opportunity to work with you. And thank you again.
Thank you.
Thank you so
Thank you. Thank you very much, participants. So I think tomorrow we have again we'll meet. We have I think first two sessions are from the doctor side. So both are from the gynec. Okay. So lots of image there. This ultrasound image, CT image. They're having lots of problem. I have already talked with Pramila ma'am, the professor of that department. So these two professors are there who is doing their MD after MBBS. One is Dr. Avinav Dasari and another is Dr. Sanskriti. After that only at 12 o'clock, Dr. Sulagna ma'am will take two consecutive class from 12 to 1:30 and 3 to 4:30. And tomorrow we have some hands-on also on CNN. So all of you, I request to join, because I want some good student. Definitely the resource person will be there. They are going to either give the assignment or they will take the interview. I don't know. They are going to choose and give to me 10 to 12 students, which is going to be assigned to all the doctors one by one. Okay, there may be some students will be there, or participant will be there in the waiting list. Nobody we can attach to them. Okay, we'll see that one, or the one student or two students, depending upon your sincerity, you can say. Okay, thank you very much. Okay, bye for today this month. Thank you.